Hi everyone. The question says that we are given an integer array nums with non-negative integers as the constraint here suggests. And in here we have two players playing optimally with player one going first. At each turn, a player can pick a number from either end of the array, either end of the remaining array. When a player picks a number, that number is removed from the array and the array shrinks. So the game ends when no numbers are left. And at every turn, um, we see the player that tries to place optimally so that they can maximize their score. And when there are no numbers remaining, the game ends. And at the end, we have to check if the score of player one is greater than equal to score of player two, which gives us player one score should be greater than or equal to player two score. So if we look at this problem and if we, let's say, bring everything to the left side, what happens? My recurrence relation becomes greater than equal to 0. So if my net score, I mean player one score minus player two score, which is let's say our net score, if this is greater than equal to 0, we return true, else we return false. So this is a classic game theory problem which is turn based, and every player tries to play optimally at each turn while the size of the array shrinks. And we have to solve this using recursion with memoization or dynamic programming. So in the first part of this, we are going to solve this using recursion. I will optimize this in my upcoming video. So in here, we are going to solve this using recursion, using memoization. So let's say at every turn, what does a player do? We are going to track the net score, which is player one score minus player two score. And in the end, we'll just say if it is greater than equal to 0, we'll return true. So let's say uh, if my start index is I and my end index is J, I have two options. Either I pick I or I pick J. What happens when I pick I? The second player would pick the best case, would pick the best optimal way in between I plus 1 to J, right? Because I've already picked I. So my array size reduces to I plus 1 comma J. If I pick J, what happens? The second player would pick I comma J minus 1. So the array of the remaining array reduces, right? So every player plays optimally. We know that. So for that particular player, will try to pick the maximum of this, right? So let's say maximum of whatever they can get. So when they pick I, nums of I would be added to the score, and the other player will, let's say, will get this from the other player. So the net gain would be nums of I minus 4. So in here, what would be added? Nums of J would be added since we're picking J, and we minus score of this. Why score of this? This is score of second player, and this is the score of first player, and we are tracking the net score, right? So we're going to pick the maximum of this and this at any occurrence. Why? Because we are maximizing, we are optimally playing, right? We want to maximize the score. So why this? I tell you the reason. Same here, why does greedy solution not work here? Let's say we have this array 157, 152, 33, 7. What happens if I pick if I pick in between 1 and 7, 7? My next player is exposed to a very larger number, which is 233. And since they're playing optimally, they will choose 233. So we might expose a larger number to them if we choose greedily. So here a greedy solution won't work. So that's why we are following this pattern here. So let's write the code. So let's say I have a function called score, private int score, It takes, yeah. So when it comes, what's the base case here? So my base case is when I is equal to j, and we have only one element remaining, so we can only choose one. So that in that case, nums of I would be added. So my I need to have two variable. I int j would be my second variable, and then I would have a nums array. So integer array nums. And then we'll use a memoization here. So integer array memo. So this is what we have. Let's create a integer array memo 2D array is equal to new integer. What's the size? It would be n comma n. So what is n? It is nums dot length, right? So it is n comma n, and we are going to return if our score of nums comma I start is 0, end is n minus 1, and memo. If this is greater than equal to 0, it means player 1 can be the winner. Now in here, what do we write? We write the base case in recursion first. What is my base case? If my I is equal to j, we just have one element left. We are going to return that particular index, nums of I, number at that particular index. Now we are going to check if my memo of I and j, if this is not null, it means we have already computed it. We had an overlapping problem, and in that case, we are returning memo of ij. And else what we are computing is we are going to compute in pick left. Let's say if I pick left, so what happens? It uh I would have nums of I, since I've picked the left, minus score of nums I plus 1, j, and memo. So this is how we get pick left. And why minus? Because we are just calculating the net gain. So here we, and our j becomes j minus 1 here. And whatever is the max, we are going to return that. So return memo of ij. And what is memo of ij? Math.max, pick left and pick right. So pick left, comma, pick right. Let's run this code. Just two test cases have passed. Let's submit this. Yes, so our solution was accepted. By the way, coming to the time and space complexity, see, if we did not have this memo, by the way, what would happen? Our space complexity would have been 2 to the power n, big O of 2 to the power n, because of all the branches. But since we have the memo, so the possible total number of possible pairs between I and j is big O of n square. So that is why our space complexity is big O of n square, and which is reduced from 2 to the power n to big O of n square. And our time complexity is big O of n square. So our space and time is big O of n square. So yeah, that was it from my end. Thanks for watching. Bye.